All right, so as you came in, you should all have gotten a little piece of paper that has your login credentials for Nabari, which is our training platform that we're going to use today. So if you haven't already gone to this URL, the instructions for how to log into Nabari are at that URL. So we will be logging into the Nabari instance, and then we will be git cloning the training materials. So actually, I can show you what that looks like. So as you go to training.quansite.dev, you'll be taken to this Keycloak login page. Let's go big. Sure. We'll talk about Nabari in just a second. Y'all just stick with me. All right, so we're going to sign in via Keycloak. You have your own individual credentials information on your little strip of paper. That's because you're going to be given your own server. So this tutorial is about big data and big data visualization. And the only way to do big data is with some machines. So we're going to give each of you an individual server, and we're going to be using Dask, and we're going to distribute that work across a lot of different Dask workers in the cloud. So we're going to use our Nabari platform to do that. So we're going to log in. We're going to click Medium Instance. And now what Nabari is going to do, Nabari is an opinionated Jupyter Hub deployment that has a bunch of extras and niceties attached to it. And it's configured in such a way that it makes deploying a Jupyter Hub deployment in the cloud, running with Kubernetes clusters and Dask and lots of other things all attached. Very, very simple. So it simplifies a lot of things. So even I'm not a DevOps person, I can deploy Nabari. And then we get a collaborative Jupyter Hub platform for your whole team, or in this case, everybody in the tutorial. So Nabari was developed by Quansite, which is where I work, and it's an open source platform. It's an open source product. You have to deploy it on your own machines, however you like to, whether cloud or HPC systems. And so now what it's going to do is it's going to reach out and tell GCP, hey, I need a server. And since we're all doing this at the same time, it's going to take a minute because GCP says, wait a second, I'm not going to give you all the machines at once. So it tries to it tries to dole them out diligently to all the people. So it might take a minute. If we weren't all hitting this at exactly the same moment, in the same span of a couple minutes, this would happen a lot faster. So like when I was testing this earlier, spun right up, no big deal. But since we're all hitting it at the same time, it takes a minute.
Sorry, are we doing the small instance or the medium instance?
You can do medium. Yeah. Yes.
What if you already click small instance and it already knows?
You can go to Home. No, you probably can't see Home. You can go to File.
Okay.
And I can't show that on the screen, but you can go to File Hub Control Center, I think it's called. And then you can log out. You can stop my server. So if you already have a small, you go File Hub Control Center. That'll take you to a page that looks kind of like this, and you can click Stop My Server and get a medium. And it's going to take a minute. It's taking quite a few minutes. There are too many of you. So while that's coming, I will just introduce myself. So my name is Kim Pevey. I am a senior software engineer manager at Quansite. So the vast majority of my duties involve software engineering and then a little bit of management of a small team. At Quansite, I do a very wide variety of things. I do back-end data analytics on big data, all the way through API creation, architecting packages, to visualization and dashboarding stuff. So I do just a wide variety of things on a day-to-day basis. My original background is in civil engineering. I did a lot of geospatial work and did a lot of numerical modeling of water resources. And that's how I got my start in Python. And I thought, hey, I like this. So I switched to Python full-time. And here I am. And this is taking forever. So this training instance is deployed on GCP, so we're actually requesting nodes from Google, and that's what we're waiting on. We're waiting for Google to actually give us individual server nodes for each of you, and it's being very dingy at the moment. I'm just going to be patient. I'm gonna be patient. You can click the event log, and there's nothing important in here. Sometimes it's like it says things that you might think, oh, like this insufficient. That it always says that. Don't be scared. That's like when it first asks for a node. It's like, hey, I don't have any nodes in my node pool. Well, yeah, because you got to request them. We'll be patient. Did anybody get a node yet? Anybody? A few. Okay. All right. Cool. So it's coming. We'll be patient. Once you do get a node, once you do get a node, you should close out all the things that you were doing right before. Sorry. Pretend like. There we go. Okay. Once you get a node, you'll be redirected to a Jupyter Hub deployment. So this is Nubari, a Nubari deployment. So now I'm sitting on my own individual server. You guys are going to have your own server. So we have our own individual server space, and then we have on Nubari we have a shared space. So if you wanted to pass a notebook to your buddy next to you, you can do that. But for today, the first thing that you're going to do is through this launcher interface, you're going to go down to the terminal, and you're going to run this git clone command. It's at the bottom of this page. So there's a git clone command to get the training materials. So on this Nubari deployment, you have a persistent NFS, so you have a persistent storage here. So it will be here if you log out, you log back in, your data will still be there. However, I had no idea how many of you there would be, and so I created just a bunch of random logins, and I didn't populate your space for you. Apologies. But so now I need you guys to populate your own space, so you can run this git clone command, and well, that's just the URL. But if you run git clone, that'll get the tutorial repo for you. I've already done that, so I'm going to navigate right in here and then go to the introduction. Okay. Now, that was a lot of setup. It really wasn't much setup, it just took a long time. But that's because we can do big data with a lot of different things, but the way that we like to do big data is with Dask. And so today we're going to teach you about doing big data visualization backed by Dask on the cloud. So all of that was required for us to get some cloud resources. I already talked about myself. What I didn't talk about is Pavitra. She is responsible for all the goodness that is going to be in this tutorial. I mean, she's done like the vast majority of the work here. I'm just here presenting. Unfortunately, she couldn't be here today, but she's a developer advocate at QuantSite. She's also part of the Bouquet core team, and she has worked extensively with the Dask community in her previous role, and she's wonderful. I wish she could be here with us, but here I am presenting solo. Let's see. I think we've already talked about this. We just need to, you're going to log into Nubari, you're going to get a medium instance, you're going to run get clone, and then the environment that we're going to be using for today is called Analyst PyData NYC 2023. So one of the benefits that we have in Nubari, using the platform of Nubari that we're all sitting on, is that we have, not only do we have shared storage space, we have shared content environments. So I've already created a content environment for us to use. That's already set up and ready to go. So that's the name of it. And next, there'll be a couple of exercises that say your turn with little computer guy. All right, so we're going to start with Dask. So the way that we're going to get to visualizing large quantities of data is through distributed computing. And that's going to be done with Dask in the background. So So we need to start by building up an understanding of what Dask is, and also what data set are we going to work with. So we'll just jump right in on the data set, I suppose. So for this tutorial, we're going to use the airline on-time performance data set, which is a bunch of flight records that were created by the U.S. Department of Transportation's Bureau of Transportation Statistics. Basically, it's an open source data set, and it covers 1987 to present day, and 23 major airlines. It's just a bunch of flight data that's tells us the flight number, the tail number of the plane, if it was late, if it was early, what time it flew, lots of different information. So it's really a great data set just to kind of play around with. So we're going to work on a subset 2003 to 2022, and that's going to be about 70 gigabytes on disk. So just to let you know kind of what that looks like on disk, this is it's in a GCP bucket, and there's just a whole bunch of CSV files. That's how the data came to us. So now, why do we need something other than pandas and NumPy to analyze this data? If you were to uncomment this and run it, which don't do that, you would crash your kernel because it's too much data. So the only thing that this here is doing is it's getting the list of CSV files, it's opening up data types JSON, and it's creating one gigantic pandas data frame. But if you try to create a pandas data frame with that much data, you're going to crash your kernel because your current server can't handle that much data. Yes?
Question. So I actually tried uncommenting and running it. Then I get a variable error. So in I think it's a list comprehension, files equal, it's asking me what FS log.
Oh, look at that. Yeah. I might have accidentally deleted that. FS is it's probably GCSFS file system. It's some GCSFS. That's right? GCSFS. Yes. So this is what we're missing. We're missing basically this from there. So it's basically just constructing a file system object to access that GCS bucket. Sorry, I must have lost that at some point. I can't say that I have run this recently. Okay, so what is Dask going to do for us? So Dask is going to provide us parallel and distributed computing in Python. So we're going to start by just talking about parallel computing. So we're going to take our work that we need to do, our compute, and we're going to distribute that amongst multiple processors. And we're going to do that through the Dask data frame API. Dask has several different APIs. There's the data frame API, which mimics pandas data frames, and Dask arrays mimic NumPy arrays. And if you've ever used Xarray, Xarray is on top of Dask array. There's also interfaces for things like lists and iterators and lots of other things. But today we're going to focus on the Dask data frame API. So that's going to be very similar to pandas. So if we run this, so we have Dask data frame as DD. So that'll be our function name. And then we're going to call read CSV just like we would in pandas, but we're only going to grab out all of the months that end in BER for now. We're going to grab all sorts of different combinations of this data. But for now, we're just going to grab these 4 months in 2020. And if we take a look at DDF, so DDF is really commonly used with with pandas data frames. So, in pandas, you might typically use the df variable. We use ddf to denote Dask data frame a lot. So if we look at DDF, what we see is it is a Dask data frame structure, but we don't actually see any data. We see some metadata about it. So we see the number of columns we see the actual columns. We see the number of partitions, which is how Dask is going to separate out this data structure. And then we have our D types. So what we don't have here is any data. And that's because Dask is lazy. It's not actually going to go out and do any computations yet. It's going to remain lazy and just build up the process of a computation and hold off on running it until we tell it to run. So it's not until we call compute that it's going to execute any computations at all. So now if we say, okay, we want to get we take the month column and we find the number of unique values in the month column. If I run that without the compute, we see that we have a Dask series object, but that's lazy. It's lazy because it hasn't actually run this computation yet. It just has an idea of how it's going to run it. So it's not until we call .compute that it actually tries to run the computation. Now, all of this is running on our server, and I can't remember what the medium instance had, but the medium instance has maybe 4 processors, maybe. So our server is, so Dask is divvying up the work amongst our 4 processors on our server for now. Now, if we run something like a .head or a .len or something like that on the data frame, that's also going to run a compute. It's going to trigger a compute. So there are some functions in the data frame API which force a compute. Now we see that we've got an error, and that's because when we ran the .head compute, it gives us an error on D types. So it says mismatch D types. So we can see that on this subset of columns, it has a certain list of expected D types, but it found conflicting D types. And the reason for this is because CSV files do not contain any information about the D types of the data. Dask is trying to be lazy. So it's trying to remain lazy and load as little data as possible. So what Dask did is it went and it read the first row of our CSV data and said, that must be the D type. And it turns out Dask was slightly wrong. And so we get this error. And so if we come on down, we actually have in our data that you have, we actually have the D type specified in a JSON file. So if we load that up, and then we rerun our read CSV and feed Dask the D types, we can see that we don't have that error anymore. So in general, CSV is not a great format for, well, not much of anything. If you're going to be doing things with big data in the cloud, CSV is to be avoided. So we'll see as we go on. We're going to switch over to Parquet. But if you do have to use CSV, it's best to specify the data types coming in. All right. Then you can take a look at the columns if you like. There's just a lot of interesting data. This is a great data set just to play around with if you just want something to mess around with. Okay, so let's talk about the logic behind Dask. So how is Dask going to do what it does? So if I tell my data frame, I want to pull the count. So I just want to count up all the records. Simple computation here, but it's going to prove the point. So what we get back, this object, this count object, Dask knows that this is going to be a series. It's going to be a Dask series, and the result will be one partition. And it even knows something about the data on there. So it knows what the D type will be, and but it hasn't actually done any work yet. So the only thing that Dask has done is it has developed a plan to do the work. So if we look at count.visualize, we can see Dask's plan, which is called the task graph. And this task graph is Dask's plan to do the work. Now remember, forgive the scroll here, but remember when we called our original data frame, and we saw that in partitions was 7, right? Even though we had 4 months worth of data, so we had 4 CSV files, Dask is going to partition this into 7 partitions. So it's going to divvy it out into 7 groups of data. Now, if we take a look at our task graph, we can see that indeed these 7 partitions are here on the bottom. So now what Dask is going to do, it's going to divvy up these individual bits of work, these tasks, onto 7 workers. If we had 7 workers, it would divvy them onto 7 workers. But it will distribute that work onto however many workers that we have in our Dask pool. And so we can see, starting from each individual chunk, it's going to take that chunk and get the count for our individual piece of data, and it's going to do that for each partition, each chunk of data, and then it's going to come back, and all of those will be aggregated together, and then it will return to me. So again, it's not going to do anything until I call compute. So once I call compute, it's actually going to run the computation. And I'm just going to let that chug while I keep talking. Any questions so far? Oh my gosh, lots of questions. You back there were first.
Can we tell Dax the number of partitions?
Yes, so you can repartition that data frame however you want.
Okay.
Yeah.
Thank you.
That same question. Yes?
The amount of workers, does it depend on the amount of core or CPU that you have?
Yes. Do the amount of workers depend on the number of CPUs you have? So right now, we didn't set up a specific Dask cluster. Dask is just going to use whatever it can find on your machine. So it's doing a lot of work for us by discovering how many cores we have on our machine, and it's going to use those. But in a minute, we'll see how we can actually set up our cluster, and we will define how many cores are in our cluster. So a cluster is going to be a group of workers that we send our tasks to. So that will be where we actually run our compute. Does that make sense?
Yes.
Okay. Any other questions?
What about what size in terms of data set would you want to use Dask over, say,
What size data set would I want to use Dask over pandas? Or okay. I mean, it just depends on the size of your machine. I was told to stand over here. It depends on the size of your machine. So obviously, once your data set starts to fill up your machine RAM, then you need to start distributing. There's some tricks that you can do. You can, if you didn't have a cluster and you wanted to stick with pandas, you would have to take, for example, one of these CSV files at a time and process it and save it out as a subset, something like that. But yeah, so the point at which you switch over to using a cluster of workers is really dependent upon your machinery and the size of the data. And the size of the cluster that you need will also depend on the size of your data. We lost one. I don't know what happened to that one.
Usually if you pull it out and plug it back in again, we had the same issue this morning in a room.
This on the HDMI?
There we go.
Ah, whew, okay. Any more questions? Yes.
Sorry, about the D types, right? So what if we have like 1,000 columns? So how do you prepare it? Like, is there any other way we can do that?
I mean, just specifying each individual one is the best. We just create a JSON and yeah.
I mean, is there a way like we can find which columns have the different D types when it says that there are different like conflicting D types?
You're saying you don't want to specify each individual column. I think you can feed in a dictionary of just the columns that you want to change.
Oh, nice.
I think.
And like, if not CSV, then what's the most used format for the Dask?
It varies widely, but I would say Parquet is common, but perhaps the most common would be something like a NetCDF, which is actually going to, for that you would use Xarray, which is going to be built on the Dask array API, which mimics the NumPy array API.
Makes sense. Thank you.
Pass it on over.
Hello, thank you very much for your presentation, for introducing us how to use big data and operate with it. Have a question about using Dask. So like previously, in my experience with like other data frames, other tools, with reading Parquet files, I face this problem that sometimes by using other libraries, like while I read Parquet files, the D types would be changed automatically. And then it's like mismatching with the original data in my file. So like, for example, when I was using Great Expectations tool, and I would need to do like run data quality checks and reading Parquet file, asserting D types wouldn't make sense because like the D types would switch. Is there a way to avoid it with using Dask? I saw that like you specify in JSON file creating library, creating dictionary, and just saying this should be this D type and this should be that D type, but that probably would override what was there in the original file. How to just read Parquet file and make sure that D types were not changed?
Yeah, so if you're reading from Parquet, you could do the same thing and specify D types coming in and overwrite. But Parquet, because Parquet saves the D type as part of the saved file, we'll see in a minute, actually, where we're going to read Parquet files and we're not going to specify D types. So it's just going to use whatever is native in the saved file.
It would be perfect.
Yeah.
Any other questions?
Okay.
Okay.
All right. Yeah, and I know I'm going kind of quick through Dask because there's a separate Dask tutorial. It was this morning. I'm sorry you missed it. Or maybe you did and you learned something. I don't know. But they will be on YouTube. So I'm trying not to like talk about Dask too much, but then also kind of got to talk about Dask because that's part of the process here. So I apologize if I'm going kind of quickly through this. It's a lot of material. Actually, this is a 90-minute version of a longer tutorial that we have done in the past, but we're trying to smush it into a smaller bit here. So I'm gonna do my best. All right. Oh my gosh, time is flying. A little bit about partitions. I'm not going to say too much about this, but the partitions in a Dask data frame are individual pandas data frames underneath the hood, which is why the API is so similar, if not identical. Anyhow, now, distributed computing. So up until this point, we have been using the workers we've been using the processors that are on your server as Dask workers. But what if we want to scale? The way that we do that is by creating a Dask cluster. So, little bit of definitions here. So we have a client, which is going to be the Python object that we interact with our cluster. That's how we are going to interact with the cluster. The cluster is going to be a group of machines. This is going to include a scheduler, which is going to manage how do those tasks in that task graph get sent to the workers, like how's that work distributed amongst the group of workers. And then the workers are just individual machines. Now, because we are operating in the cloud, we are going to use another tool called Dask Gateway. And Dask Gateway is going to provide an interface for us to create a Kubernetes cluster of cloud servers. So these servers, these worker nodes may have, so each worker node may have its own individual scheduler, or we may just have a worker node with several processors on it. So that may have, I don't want to get into too much of these details, but just know that Dask Gateway is what is managing our cloud cluster of worker nodes. And a worker is just going to be a machine. It's just a cloud machine at this point. And then we're going to have a scheduler that's going to distribute that work out to the individual workers. So let's create a cluster. So this is how we're going to set up our cluster. We're going to feed it some options. So we have, since we're working in a Jupyter Notebook, we have a couple of different options. This environment is a conda environment. So when you have all your workers and you're going to send this .compute out to each individual workers, you have to actually specify what is the conda environment that's going to run. And so here we have a list of all the environments that we have on this Nabari instance right now. But you guys already have, hopefully, the right one selected, which is Analyst PyData NYC 2023. And then we're going to ask for a medium worker. So the other thing that we can specify during the Nabari configuration setup is exactly what size workers do we want. So here we're just going to use the medium worker again. And then also we can pass environment variables to our workers because our workers don't have the same file system that we have that we're sitting on. So not only do we have to send our data to the workers, and our workers have to have an environment to work in, but our workers might need access to like S3, for example. So you may need to send it environment variables. Now we're going to create a new cluster. And we see we have a cluster widget here. So we can either adapt manually we can either scale manually or use adaptive scaling. So the manual scaling is when we will say, hey, Dask, I need 10 workers. I want you to go out and get those cloud worker machines, and I want you to keep them until I tell you to let them go. But you can imagine that's not super efficient. And we try to be judicious with our compute clusters, our compute resources. So we like to do adaptive scaling. So you set a minimum and a maximum. Usually, like if I was working on something like for real, I would set the minimum to be 0 and then the maximum to be like whatever the maximum number of workers that my compute needed. But for this example, so that we can all kind of start asking for workers because it's going to take some time, we're going to set a minimum of 5 and a maximum of 10. And you're going to click Adapt, and it's going to start to request those nodes. Now, we're going to get ourselves we're going to connect that cluster to a client. Now, we get a dashboard URL here. So if you click on this dashboard URL, that takes us to that takes us to the dashboard. The other option you have is on this Nabari deployment, we have the Dask Jupyter, where did the word go? Jupyter Lab extension. So if we can paste in the URL of our worker, and if you have spaces on the end of your URL, it won't work. It's kind of finicky. So just make sure you don't have any spaces back behind status. And this gives you the same thing that you see in the dashboard. You can click on these and get them inside of your Jupyter Lab interface. So now I can like stick this down here at the bottom and we can keep an eye on it. I also like cluster map. So this is cluster map, kind of shows you how many nodes that you have. Yeah, okay, I'm just gonna keep on trucking. We have a quick computation here. Yeah, I think I'm just going to kind of run through this example because we have a lot of stuff to cover. So if we calculate the maximum distance and run a compute on this, I just want to talk about the dashboard for just a second. We can see that the cluster map will start to add additional nodes as Dask feels the need for more nodes to handle that compute. Dask will start to add more nodes. And then we can see what's actually happening here. This node in the middle is the scheduler. And these nodes around the outside are worker nodes. And so we see data being transferred back and forth. We didn't need very many nodes, obviously. That was an easy one. We also see this task stream. And yeah. Okay, so we saw, I'm gonna run that one more time. And I'm gonna switch over to this Dask dashboard. And so we can also see through this interface, we can see the bytes stored per worker. So this is how much worker memory is being used. And here, if we watch this, you start to see that your workers are filling up with memory. Once your workers start to get full of memory, that's when you want to start scaling more. So you need to add more workers at that point. And you can also access the task graph here through this interface. Yeah, all right, well, let's keep going because there's more stuff on the next notebook. All right. Okay. So now we're going to actually work with some bigger data. All right, so for now, we're gonna run our Dask gateway object again. And this time, we're gonna create our cluster programmatically. So you don't have to use the widgets if you don't want to. You can do all the same things programmatically. So if we run this and one thing to note is even though we specified .adapt here and we gave it a minimum and a maximum, it's going to do that. It's going to adapt, but it's not going to show up the 5 and the 10 here in the widget. You just got to trust it. Just trust. All right. So now you see our cluster map down here. Our widgets at the bottom didn't populate. That's because we have a new URL. So we have to take our URL and repopulate here. And make sure you delete any spaces at the end. And our widgets will update. Okay. Now we are going to read the full data set, which has been resaved as Parquet. So part of the very first part of this process, or working with this data, is we took the CSV files, we assigned some D types, and we saved it back out as Parquet so that we had a data set that was a little easier to work with. So now if we have, if we call read Parquet on this data, we can see it's the same data as we had before. Now, I'm gonna run this. Actually, I don't have enough real estate. Oh, goodness. Okay. All right. So when I run this, let me just say, what are we running? We're doing a group by flight date. So we're going to group by flight date. We're going to pull out the canceled column, and we're going to get a count. And then we're going to plot it with HVplot. More on HVplot later. But just to kind of look at this just really briefly, this is going to take a long time to compute. And we're going to see that when we get a result, our plot looks kind of crummy. And the reason why is because HVplot has received all of this data from all the different chunks out of order. So this is your typical, it's trying to plot a line plot, but all of the chunks came back out of order. And so, what we're going to do is we're going to have to sort the data before we plot it. But something like sorting, setting the index, those things are data set wide processes. So these require something called shuffling. So we have all of this data that's distributed across all these workers. And the only way to figure out, for example, the only way to sort something is to actually touch all of the data. There's just no way around it. So whenever you're working with distributed computing, you want to minimize the shuffling of data. So usually what we do is if you have to do that as part of your workflow, you do that once and you either save it or persist it on disk. So here we have already sorted the data. So this is the sorted version of this data, and we're going to save it out so that the next couple of computations are going to run a little bit smoother. Do I have until 2:30? Is that what it is? Yes? Okay. Okay,
Question.
cool. Yes.
Are you saying that if you sort your data and save the state of the data, it will be faster? Right? It won't reshuffle.
It will shuffle it.
Right.
It will shuffle it, but then you have to save that state.
Exactly.
Either save it to a file or persist it on disk, which we're going to talk about persisting data on the cluster here in a second.
Okay.
All right. So now rerun this previous computation on the sorted data set. I'm going to go ahead and do this because I need to talk faster. This is a lot of information. So now if we rerun that same computation on the sorted data set, it goes a lot faster. We see a lot less little red bars. So in our task stream where you see red, that's actually the nodes communicating with each other. So when we distribute the work amongst multiple workers, those workers have to talk to each other, right? They have to re-aggregate that information. Okay, now, persisting data. Yes, I knew we were gonna get there. Like we said, there are some tasks that you do that are computationally expensive, and we don't want to recompute. For example, reading the data and transferring that data from wherever it lives onto your cluster is going to take a lot of time. So just data transfer on the reads is time consuming. So one thing that you might want to do is persist the data on your cluster. So you have your group of worker nodes. You want to read the data. Dask is going to distribute that data onto your worker nodes, and you're going to persist. So you call like .persist, it is in Dask. And Dask will actually leave that data on the nodes. So as we saw our cluster map and our cluster memory, as we ran this computation, Dask was reading data, it was doing some computation to some small subset of the data, and it was letting that data go as it re-aggregated and sent the result to us. But we can also tell Dask, when you read the data and you do some stuff and you send some information back to me, I want you to hold on to that data, like don't let it go. And so we do that with persistence. Apparently I have examples here. Who knew? Who knew? Can't keep up with myself. So if we run these two aggregations, so we group by flight date and pull out departure delay, we're going to count the total number of departure delays by date, and we'll compute the arrival delays by date. This is without persistence. So what Dask is doing, let me find this. Just go right here. Right, so what Dask is doing is it's going to run this compute, bring all the information back together, and then once it has that information and it just runs all the compute and sends it back to me, it's going to let all that information go. So now all of that data has been essentially purged from our cluster. All right, so that took us, where were we? 25 seconds for one, 23 seconds for another. Now, if we took if we took this data set and we persisted this data, now what we're doing is we're going to take all of our data and we're going to put it on our nodes, and we're going to just leave it there. So what we'll see is it's going and gathering up data, and our workers are filling up. So here's the number of workers that we have, and slowly these numbers are creeping up as we store data on our worker. Okay, now if we run the same compute, we run those same two computations, now we see that it only took us 2.7 seconds and 1.67 seconds, because all the data didn't have to be reread, because reading data from disk and transferring it to another cloud server is the most time-consuming part of this. Okay, now a little bit about partitioning. You know, I'm going to skip over this partitioning bit. Right now we have 641 partitions. We can reorganize our data by partitioning it differently. So this is like telling Dask exactly how many chunks of data to separate into before we send it to the cluster. I'm gonna let you guys do that on your own. We also have a meta keyword. I'm just gonna breeze through this because I wanna get to visualization stuff, and I've talked about Dask too much. I knew that was gonna happen. I also give a whole workshop on Dask and X-Array, so I have a lot to say. But I want to get to visualization. So there's also a meta keyword here, which helps us to help Dask predict. So kind of the same situation where D-types, with the D-types, Dask tries its best to make an assumption, but there are some cases where Dask just doesn't have enough information to make a good prediction. And so we can send it metadata. In this case, we're telling it, hey, I want you to know this is going to be a pandas series once it's done. Okay. So let's move on to visualizations. It's much more fun. All right, so our big data visualizations here. Let me minimize that real quick. There's just not enough space. Okay. Yep. Okay. So for our visualization, we're going to use a tool called HVplot. And HVplot is part of the HoloViz suite of tools, and they give us some interactive visualizations, both in the notebook here and just in like web apps or things like that. And it can be backed by either Bokeh or Matplotlib or Plotly. And so HVplot is kind of a simplified version of HoloViews, and what HVplot does is it kind of mimics the dot plot functionality that Pandas has. So if you're familiar with Pandas and you've ever done a dot plot and it gives you a quick visualization, HVplot is going to be something similar. So super high level API, and it's currently built on these data libraries. So it works with DAS data frames, Xarray, Pandas, GeoPandas, all those that you see here. So if we get ourselves a cluster, and this little snippet, just if you already had a cluster running in your other notebook and didn't shut it down, this will go and grab that cluster. And if not, it'll create a new one. But if you did have a already running cluster that it connects to, sometimes you have to refresh your dashboard page. All right, so going back to our flights data. Small caveat here. We're taking some subsets because all of these HVplot examples that we're going to see here will work if you have a very large cluster, but this is a huge data set. And so we're going to take a small subset of the data set so that we can all run this on 10 worker nodes. But feel free to adapt. So now we're going to filter by year. So we're going to filter to greater than 2020. And we're also going to filter by the carrier name. So American Airlines, United, I don't know what WN is, and Delta. All right. So now if we want to look, see what's happening. Why is that not loading? Okay. Oh, I don't have any workers. That's why that's taking a long time. I probably shouldn't have shut down my cluster. Yeah. So one thing, just like when we were spinning up nodes at the beginning of class, GCP is like, it only wants to give out a certain number of workers at a time. It's almost like rate limiting you on workers to a degree. So sometimes I find that when I teach these classes, I have a hard time getting workers back, which is why I put that little thing in there where you keep your cluster alive. But I don't have any workers, so I can't actually do any work. I might have to invite somebody up to the stage. Who knows? We'll give it a minute. Questions? Questions? No questions? No? I don't know why I'm not getting workers. Does anybody else getting workers? You guys have workers? Yeah? At least one? All right. Yes?
When you are partitioning data, is there a method to partitioning different types of data? Namely, there's calculated data, and then I'm thinking of text, but long, lengthy text.
Yeah, so there's a complicated answer there.
Okay.
So Right now, we're just working with the Dask data frame API, which is going to partition based on rows. If you're using the Dask array, the interface, and you have a Dask array, so you have a multi-dimensional array, then instead of partitioning, it's called chunking. So you're chunking in multi-dimensions, which then gets a lot more complicated. So then I could talk for an hour on chunking and how to chunk data, but it's very specific to what data you have. So if you have time series data and you're going to be doing like time series computations, you want your chunks to follow along with your time series, like a series of like a time series at a given node, like on gridded data, for example. If you have gridded data and you have a time series for each individual node on the grid, you're going to want to chunk so that each grid node has all the time series at that grid node in a single chunk. I don't know if I explained that well.
I got it. Thank you.
Chunking is like, you could spend forever on chunking because the efficiency of how you read and write your data and compute on your data has a lot to do with how you chunk. And the data frame interface is a little simplified because it's based on pandas, so it's just partitioning based on rows. Yeah. And I have no idea why I'm not getting anything, so I'm just going to restart because Jupyter is like, sometimes you just start over. Actually, you know what I'm going to do? I'm going to force it to give me a new cluster. Hold on. Whoops. Start fresh. Give me a new cluster. Close this out. I'm not sure what is happening right now. Well, so I'm wondering if somebody else wants to come share their screen. Why I can't, I have no idea why I can't get a cluster running. Goodness, what do you do? Patient, does anybody want to come share their screen? Does anybody?
You refresh the window.
This one?
No, the other one's the back.
Oh, I could.
Yeah, because sometimes when you're in if it gives a command, then it won't go talk to the server. If you know what I mean.
I don't think it's like, I don't know what's happening right now, honestly. I feel like I just want to restart, which is like, that's my only fix. Come on. So if I say list clusters, so I have a cluster pool. So
You executed everything before the cluster.
it says I have a cluster pool. Let me just see. It's created the cluster pool, but I don't have any workers in my pool. So for some reason, GCP does not want to give me any workers. They're on to me.
You specify basically how many worker you wanted?
I specified through the API. Well, actually, yeah, right now I'm just getting, actually what I can do. It's a good point. Well, we have 9 minutes left, and there's a lot of stuff here, but I can't actually visualize this. Oh my goodness. Yeah, I would love to use your computer. Thank you.
We have half an hour.
We have half an hour. We don't have half an hour. Do we have half an hour? 2:50. Oh gosh. Whew. Okay. I feel better now. Okay, here we go. The coloring is very funky, and I'm not sure why. I think I'm just gonna. We'll be all right. We'll be all right. I think it's okay. I'm not sure how to change the coloring on the display. Okay. All right. So now we're going to put HV plot on top of Dask. So we kind of saw the same visualization a second ago, where we're going to group by the flight date and capture the total number of departure delays based on the date. So if we take a look at this, we just put .plot back here, and HV plot is going to look at what type of data we have, and it's going to make its best guess as to what style. So it's going to look at the data and say, oh, okay, I'm going to plot that with a line plot. This is a fun data set because you can really see a lot of very strange things. If we plotted in 2020, you could actually see the drop off when COVID, everything shut down. I'm going to skip over this part. I'm going to skip the your turn business because we took enough time with that. But here we are going to calculate the mean of the arrival delay based on the day of the week. And we're going to put that on a scatter plot. So all we have to do is we have to call .scatter here, and then we're going to tell HV plot to put day of the week on the x-axis and arrival delay on the y-axis. And we can look, there's a link here to the HV plot gallery. I did that, now I'm not sure how to get back.
Command S. Command
S.
Aha. Command S.
Sweet, thanks. All right, so you can look through the HV plot gallery to see what different plot types they have. So one of the really great things about HV plot is that you can get widgets to lay on top of your visualizations, or to link up with your visualizations. Very simple, in a very simple way. So here we're going to create a histogram, and we're going to group by. So this group by is telling HV plot that I want a widget, and I want a widget based on this OP carrier. So it's essentially doing, in the background, it's essentially doing a pandas group by, but it's going to give us a widget to interact with. So, do we persist this data anywhere? Probably. Oh, we did persist. Okay, good. So, what it's going to do is it's going to HV plot knows how to interact with the Dask data frame, and it's going to do its best job to run its computations in a lazy fashion as much as possible, but it is gonna have to run some computes. So just like we talked about, like if you run a .head on a DAS data frame, it's gotta run a compute in order to actually return some data. And so the same thing with HVplot. HVplot at some point is going to run a compute. And so we'll see that it does a compute for every carrier. So here, if we change our carrier, so it gave us a free widget, so we get a free widget that's connected to our visualization here, which is interactive. But when we change the carrier, we see that it's going to rerun our compute. And so when we create visualizations based on DAS data frames, we need to think about exactly how that data is persisted on the cluster, and what's the best way to store the data so that we do minimal recomputes as we interact with the visualization. So it's sort of the good and the bad, right? So HVplot gives us interactive components to our visualization, but then also it's interactive. So how much do we pre-compute ahead of time? All right, another great thing about HVplot, we can compose and overlay plots. So we can have multiple plots that are linked together. So I'm gonna run this, and I'm going to persist this data. So here we're getting our subset. We're gonna do a group by for day of the week and OP carrier. We're gonna pull out departure delay, and then we're gonna aggregate it in 3 different ways. This is just the same as pandas.ag, right? We're just gonna aggregate it based on the minimum, the mean, and the maximum. And then a little note about the rest of this. This is like two commands that you don't want to have to do very often. So reset index is computationally expensive because it has to touch all of the data. Sort values is computationally expensive because you have to touch all of the data. But at the moment, DAS data frames does not support multi-indices. So what's coming back from everything on this side, everything on that side, is a multi-indexed data frame. But because DAS doesn't work with that just yet, we're gonna reset the index, and then we're gonna sort values so that our visualization looks nice. And then once we do all that, we're gonna persist the data because we don't wanna do that multiple times. So here we're gonna get a min-max plot. So we're gonna plot an area plot. So we're gonna have day of the week here on the x-axis, and then on the y-axis, we actually have 2 y-axes, or 2 things visualized on the y-axis. We have the minimum and the maximum. And then we specify our alpha, so this is your opacity. And we're gonna give ourselves a free widget. So group by carrier. And then we can also, this HVplot area, we can either stack them or unstack them. We can provide a legend. It's an excellent question that no one asked yet is, where's my legend? I have the same question. See me after class. All right, so here we compose this area plot. We have a widget that if we change our carrier here, we interact with our widget, our visualization will automatically update. Great. Now, supposing we had another, another plot. And here we're gonna plot just a scatter plot. We're gonna give it day of the week on the x-axis and the mean for the y-axis. And we're gonna do the same thing with our widget. We're gonna group by OP carrier for our widget. So now we have another visualization, but we have the same widget, all right? If we use the plus operator for HVplot, what that will do for us is it will plot those 2 plots side by side, And the other thing, oh, we're just gonna have to minimize here so you can see. Okay, so if we use plus, that will plot multiple plots side by side, but then also notice that we just got one widget. So hvplot understands, it was able to understand that we have the same widget that's trying to access or controlling our visualization, so it combined them. So now this one single widget is going to control both of those plots. We also can provide this star operator, and that will tell hvplot to overlay the two visualizations. So now we're going to overlay our minimum and our maximum. What were we looking at? I don't even know anymore. Departure delay, depth delay. Golly. Okay. So now we can overlay these two together. So we see the absolute minimum departure delay for the day of the week to the maximum departure delay for this Delta carrier. So we can see there's a pretty big range of departure delay. I mean, at some point, it's not a delay anymore, it's just canceled, which we have data for. But that doesn't really tell us much. So let's overlay the mean, and we can actually get an idea of where the mean actually lies, which is a whole lot closer to the bottom here. And then it's interactive, so we can actually play around. I was really surprised to know that planes leave early, according to this data. Oh, you got me. But anyway, all right, moving on. So we've kind of gone over different ways to create these HV plots. Now there's, you can go look through the docs for HVplot to see what sort of parameters you have available to mess with. For example, the alpha or the color or things like that. Or the other thing that hvplot provides is this Explorer interface. So Explorer is a GUI interface for constructing your plots. So say you just wanted to, you didn't feel like looking through the docs and just wanted to mess around with how to generate your plots. You have this little Explorer GUI, and this helps you to define you can define your plot through this interface. So you can specify what do you want on each X and Y. You can group by, you can specify the type of plot, and you can see the default plot was a mess, right? So I don't know. So you can play around with all the different options that are available in hvplot without having to know exactly what plot options are available at any given moment. So this is just kind of fun to play around with and sort of build your own as you go. I will say you can get yourself into a bit of a pickle here because you are doing by and group by or group by operations underneath the hood. Group by gives you a widget. By does the same thing. It does a group by, but it doesn't give you a widget. And so because it's doing that kind of compute on the back end, you can end up crashing your kernel because you've tried to compute too much. So we've sort of run this on a subset, but just be aware when you're playing with this and you're trying to build your graph, it's best to do it on a smaller subset. And then when you're done, you can save your plot, or you can generate the code for that plot. So now you've got your plot looking just like you want it. You can either save this plot out, or you can click on code and go and grab the actual code that you would need to recreate that plot. It's pretty fun. Oh, look at that. this is my fault right here. I neglected to add one of these. Sorry. Your conda environment that I gave you is missing a package. So you can't save, but you can. See, I could just add that. I could add to the conda environment really quick, and then we could all. Oh, I wonder if this will. Oops. So the good thing about Nabari is that, no, that doesn't work. The good thing about Nabari is that we can all share a created conda environment. The bad thing is if somebody changes the environment and doesn't tell you, you all don't have it. Oh, goodness. All right. Let's talk about geographic plots really briefly here. All right, so now we're going to steal this CSV file here. It's not stealing. They shared it. They meant for us to have it. But it's latitude, longitude locations of U.S. airports. And we're going to combine that with our flights data. So this is what the data looks like. All of the airports have these airport codes. And we're going to combine that with our flights data to get latitude, longitude for our flights. We're going to persist that on our cluster. And now, if we run .hvplot.points, we can get a visualization of that data backed by a geographic map. So this is using a web map tile service back behind our image. So we tell it longitude, our longitude column is going to be X, latitude column is going to be Y. And then when we say geo equals true, that's letting hvplot know that this is a geographic data set. So it knows it's going to be plotting latitude and longitude. So the visualization here is not skewed, it's reprojected properly so that we get our typical, what we would typically expect from a map. And then the other thing we can do, we can specify tiles. So there are a variety of web map tile services that are available. I like Carto Lite is a good one. If you're doing visualizations and you don't want to mess with the colors. So like, sometimes color can, you don't want a colored background if you're going to be examining your color map. Right. So we can specify our color map is based on departure delay, and we can give it xlim and ylim for the initial visualization. And this little button here, all of our plots are backed by Bokeh, though if you wanted a matplotlib or a plotly image, you can also use that backend. But in Bokeh land, this little circular guy will reset your plot to the original extents. So that would be whatever xlim and ylim are being set for. All right. Lastly, plotting large data sets. So all of this has been plotting large data sets, but thus far, we've done this in such a way that we've used Dask to sort of pre-process a lot of our big data before we got it to visualization. But what if you have a lot of data and you want to send a lot of data to your visualization to be visualized? So here we are going to use Data Shader. I'm not sure why I would read. Okay. So our full data set has 125 million rows. So for this data set, for this example, I'm just gonna pull in a subset, but if you want to use this bigger data set, you certainly can. You're probably gonna need more nodes for that. but GCP has to give you those. But anyway, so we can run all of these visualizations on the full data set. It's just for a matter of time and number of worker nodes, we've downsampled a little bit, just so you know. All right, so what Data Shader does, Data Shader is also in the HoloViz suite, although it's built and maintained by the same folks at Anaconda. Great people, by the way. But it also, it can be applied outside of the HoloViz suite. But for us, it's a first-class citizen in the HVPlot API. So here, if we want to do a line chart and we want to have flight date on the x-axis and departure delay on the y-axis, that's actually going to be a lot of data, right? So we have 30 million rows, and in order to visualize 30 million rows of data, if you send all that data to the browser, your browser will crash because your browser just simply cannot handle that amount of data. So what Data Shader does is it's going to downsample the data before it gets to your browser. So our visualization, our image that we're going to create is a certain size, some pixel by pixel size. So it's 600 pixels by 800 pixels. What Data Shader is going to do is it's going to downsample the data at each individual pixel. So it's going to aggregate what would have been behind that pixel, and it's going to aggregate based on a variety of different methods. So you can either tell it to aggregate based on the total number of counts, or you can aggregate based on the mean. That's taking a while. So the total amount of data that gets sent to the browser is then only the size of the actual image, the total number of pixels. So all of the work is being done on the Python side, behind the scenes, and we only have to send a smaller amount of data to the browser. Well, while that's thinking, do you see how many red blocks we have in our task stream? It's doing a lot of transferring. So each red block is a transfer, either between nodes or between the node and the scheduler. And anytime you see a lot of those, that's kind of a warning sign that you're not doing things very efficiently. So it's spending a lot of time talking. It's spending a lot of time in communication and transferring data. I'm also not really sure why is it still thinking. Oh, I know why. Because as we pan and zoom, it's going to have to re-render. More on that in a sec. Okay, so what this has done is it has plotted our 30 million row data set all on a single plot. So now we have every single data point is on that plot. But what we've done is we've downsampled it so that the only thing that actually came to the browser was the color of the pixel. So the color of the pixel was based on the aggregation of the data on the back end. So that was done by Python. So we can also do this with a scatter plot. And then lastly, we have some different options for how we aggregate the data. So we can either aggregate based on the mean, the count, min, max, and more. So here, if we just change our aggregator, we can see we get another option. I mean, this is a different plot, but here we're just doing a scatter plot with a different aggregator.